Continuing our look at inverse functions, let's talk in this video lecture about how to find the inverse function of a given function. Our objective then, obtain the inverse function both algebraically and from the graph of a given function. Okay, we know what an inverse function is. We saw that in our previous video lecture. An inverse function is a function that undoes a given function. Okay, we talked about its notation, that this little negative 1 just above and to the right of the function's name, the f function or the g function here, tells you it's an inverse, and remember, this is not a -1 exponent. The -1 to the above and to the right of the name means it's inverse. And we also saw that the domain of the function is equal to the range of its inverse, and the range of the function is equal to the domain of its inverse. Let's first talk about graphically, since that seems to be a little bit easier. And let's take a couple that we already know, and let's examine what takes place. Okay, I should say we already know their inverses. So we worked with these in our previous video lecture, and so we know that the graphs of x cubed and the cube root of x are inverses, or the functions. The functions x cubed and the cube root function are inverses of one another. Let's look at their graphs. Okay, so I'm going to do, and you noted here I put in here the function, I'll put it in as y1, and the inverse of the function I'll put in as y2. Okay, so y1 is x cubed. y2 is the cube root I happen to have under my math menu. Number 4 is the cube root option, so the cube root of x. And I'll press graph here on the standard screen. There's x cubed, and here comes the cube root of x. Okay, one thing you should, hopefully what you notice here is that there's some symmetry going on. Okay, this one came in and did a little dipsy-do around, went flattish and then back up. This one came in. This one went vertical, so this one went horizontal and back up kind of. This one went vertical. The red line went vertical and then back horizontal. So there's some symmetry here. I'm gonna put in the line y equals x as y3. Okay, so y3 is can be a black line in this case, and here it comes. And you can see right there that these two graphs are symmetrical about the line y equals x. Let's zoom in a little bit more to where things get kind of interesting here near the origin. Let's just come in a little bit so we can see that just a bit more clearly, that there's actually symmetry. Whoops, I got to put that as a 5, not a -5. So here comes y cubed. Here comes the cube root. And here comes y equals x, going right through, symmetrical about. Okay, a little hiccup here for some reason. That might have to do with my pixels. But you can see the symmetry. This goes to here, this goes to here. The origin's in the same place. Red goes to blue, blue goes to red, blue goes to red, red goes to blue, red goes to blue. It is symmetrical about the line y equals x. Might help a little bit more even if I press squaring. If I make the screen square, there's y equals x cubed. Here comes y equals the cube root of x. And again, here comes y equals x. And again, you can see the symmetry. Okay? Now, let's do this again. Okay, let's do this again with this example. And again, we know that the function 2x plus 6 and the function 1/2 x minus 3, we saw this in a previous video lecture, that these are inverses of one another. So let's look at their graphs and see if the same thing takes place. So y equals, I'll clear these, I'll leave y equals x in there. Okay, so I have my first equation, y1, I'll do as 2x plus 6. and I want to do y2 as 1/2 of an x, and I'll subtract 3. So there's my first line. Here's my second line. Whoops, I'm missing a little bit, so I need to go zoom out. And here comes the line. Okay, that's not helping me too much because I was too zoomed in. So let's go back to my window, and let's go back to -10 to 10 in my window so that I can see the lines actually crossing. Okay, so here's the first one, 2x plus 6. Here's the second one, 1/2 x minus 3, right here. And here comes y equals x. And again, pretty clearly, they're symmetrical. Okay, they intersect here, but the distance that the red is from the black is equal to the distance the blue is from the black. The distance of blue from black is the same as red from black. So they are symmetrical about the line y equals x. Okay, so graphs of inverse functions. They are symmetrical, S-Y-M-M, no, S-Y, symmetrical, I think it's 2 M's. I think it was only 1 M. Me and my spelling. Symmetrical, no, there are 2 M's. Symmetry, S-Y-M-M. About the line y equals x. So we can now, if we wanted to, we could also add this into our list of what we know about inverse functions. Okay, the graphs have symmetry, and they are symmetrical about the line y equals x. So it's not too difficult working with inverse functions because your graphs are symmetrical. Okay, let's find inverse functions algebraically. Okay, so we have an inverse function. We don't have we're not going to look at the graph, and we want to find its inverse algebraically. Okay, in other words, if I give you f of x, find its inverse, the inverse of f of x. Okay, how we do this is fairly straightforward. What makes it easiest, so step 1, I suggest replacing the f of x with a y. It just makes things a little easier as you do some algebra to have one letter as opposed to this notation here. Step 2, solve the equation for x. Step 3, you're all done with this. Replace the y with an x and replace the x with the inverse function of x. And then step 4, verify by showing that this is true, which we saw in a previous video lecture, and this is true. Okay, if those two things are true, we know that our algebra was done correctly. Okay, let's look at 2 examples for this. We're going to look at the same example, x cubed. We're going to find its inverse algebraically. We already know its inverse is the cube root of x. We've already verified this. So we're just going to look at steps 1 through 3 in this case. Okay, step 1, replace the f of x with a y. All right, y equals x cubed. Replace f of x, that's a terrible f, sorry about that. Replace f of x with y. Okay, now let's solve for x. Well, x is being cubed, so I'm going to cube root both sides. And the cube root of x, I've just solved for x, is equal to the cubed root of y. And I'm going to write it, I'm going to put x equals, I'm just going to reverse it because it looks more normal to us to go like this. Okay, so this. All right, I just solved for x. Okay, x equals the cube root of y. Step 3, replace the y with an x and the x with an f negative 1 of x. Okay, replace the x with an inverse of x and replace the y with an x, and we just found the inverse. And again, I'm not going to verify because we did that in a previous video lecture. I think in the last one we looked at properties of inverse functions. So there's how you find the inverse algebraically. Let's do another example that's a little more complicated, that takes a bit more algebra, and then we'll also do a verification on it. So it's going to take us a little bit of paper. I'll use the bottom half of this one and the top half of the next sheet. Okay, so my function f of x equals 2 divided by 3 plus x. Find the inverse algebraically and verify. All right, step 1. Let's replace the f of x with a y to make things a bit easier. So y equals 2 over 3 plus x. Okay, let's see here. Get my notes to make sure I'm not going to make a mistake. Okay, I just replaced f of x with y. Okay, we're good there. Now let's solve for x. I'm going to multiply both sides times 3 plus x to get rid of this denominator. Okay, and then on the left side, I have 3y plus xy is equal to 2. Okay, no more fraction. That's kind of nice. I'm going to subtract 3y from both sides. Remember, I'm solving for x. Here's my x right here. So on the left side, I have x times y equals 2 minus 3y. And then to get x by itself, I'm going to divide both sides by y. And I have x is equal to 2 minus 3y divided by y. So I just solved for x. Took some algebra. Well, we can do that. All right, step 3, replace y with an x and replace x with f inverse of x. So replace the x with the inverse symbol and replace my y's, so 2 minus with an x. Okay? Replace y with x and x with the inverse of x, inverse function of x. And there you have it. There's the inverse. Okay, so we think, assuming all is done well, we think that this function, the function that'll undo this function is this function. All right, so if 0 goes into here, out comes 2/3. If 2/3 goes into here, then out should come 0. We should be able to, these two functions should undo one another. Let's verify that. So I'm going to turn this over here. Whoops, I'm going to get another piece of paper out. And I'm going to continue this example with our verification. So A, continue. Whoops, that's not what I wanted to do. Okay, I want to continue A and verify. Okay, let's recall. We say that f of x is equal to 2 over 3 plus x. Okay, and we're claiming that its inverse is equal to 2 minus 3x over x. We want to verify this is true. Well, first, okay, I will do, just a second, my pencil and my lead are, okay, first, what is f of? The inverse of f of x. Okay, this should give us x, all right? So the inverse function, so what is the function's value when I put this into it? 2 minus 3x over x. I bet you're shaking your head right now because this is going to work with some fractions. This is probably going to be reasonably complicated. Okay, let's see now. So this is the input that goes into this function. So this is going to be 2 over 3 plus this, because that's what it says. 2 over 3 plus the input. And this is the input. 2 minus 3x over x. How delightful is that? A complex fraction to simplify. And supposedly this all equals x. Well, let's see. I'm going to do the denominator first. I'm going to leave 2 in the numerator. Different ways to do this. I'm going to find a common denominator of x in the denominator. And my numerator is therefore going to be 3x plus 2 minus 3x with a common denominator of x. 3x over x is 3. So that's fine. Okay, now let's simplify that denominator a little bit. My numerator is still a 2. 3x plus 2 minus 3x is 2 over x. Okay, and I know that 2 divided by 2 over x is the same as 2 times x over 2, which equals x. I got it. Okay, again, I should have gotten that when I do the function. If I take the function, a function of the inverse, I should get back out the x. I should get back out what I put in. This is the input. When I do the function of its inverse, I should get the input of x right back. Let's do the opposite of that. We want to take the inverse, this is verifying, of the function. And we should also get an x back out. Okay, let's see. This is the inverse. Well, the function this time is the inside, which is 2 over 3 plus x. 2 over 3 plus x. Okay, so this is my input. And it should go, this now goes into the inverse function, which means it goes here and here. Oh my goodness. So numerator, 2 minus 3 times 2 over 3 plus x divided by x, this is the input, 2 over 3 plus x. Well, yippee skippy. That's a lot going on there. All right, let's take our time here. Let's look at the numerator. So let's see here. This is 2 minus, I'll put a 6. I'm going to simply distribute this 3. So 2 minus 6 over 3 plus x divided by 2 over 3 plus x. We're testing my, we're certainly testing my algebra skills here. I need a common denominator in the numerator. So again, I'm going to come down one more line. Okay, here's my big fraction. I need a common denominator. I'm going to use 3 plus x as my common denominator. My numerator is going to be 2 times 3 plus x minus 6. Okay, so this divided by this is 2, and this is this fraction here. All of that over 2 divided by 3 plus x. Okay, let's simplify the numerator. This is 6 plus 2x minus 6. So this is 2x over 3 plus x. All of that over 2 over 3 plus x. Okay, so now I have a division of fractions problem, and I'm good with that. So this is 2 over x divided by 3 plus x times the reciprocal. 3 plus x divided by 2. Well, look at that. Common factor, common factor, common factor, common factor, and out comes the x. I just verified. Now, it took a number of steps. Took a lot of, in the verification, took a fair amount of working with fractions in algebra. It wasn't the nicest stuff to do. I certainly took my time, and I certainly used a lot of space to make sure I could write my numbers clearly. Excuse me. And work my way through it as best I could. Okay, now what is the domain? Let's. I want to keep it right here. Part B said domain and range. Well, the domain, I think I have no space down here. I can see the functions at the top of the screen. The domain of the function is equal to the range of the inverse function. Okay, well, the domain of this function, okay, is all x's except -3. Right here. Here's the function. This is a rational function. It'll take any x you want, but a -3 will make the denominator 0, and so it won't take -3. So the domain of this function is all x's but -3. Well, the range of this function means any x but -3. Okay, and the range of the f function is equal to the domain of the inverse function. Well, let's see here. What's the domain of the inverse function? The inverse function is right here. All right, the inverse function, again, it's a rational function, and the only x you can't use is 0. So the domain of the inverse function is all x's except when x is 0, which means it's also the range of this function. This function will not, you can't get 0 to come out of it. It's not part of the range. You get any other number you want to come out, but you can't get 0 to come out of that function. So there you have it. Looking graphically, inverse functions are symmetrical about the y equals x line. And to find an inverse function algebraically, you basically, in a nutshell here, you're switching x and y and solving for x. And you'll come up with the inverse function algebraically.